Let's look at a few more examples of verifying trigonometric identities. Here we have 1 plus sine y times the quantity 1 plus sine negative y is equal to cosine squared y. So again, we're trying to make the left-hand side of the equation equal the right-hand side of the equation. Well, one thing that jumps out at us here is that we have a negative inside of this trig function. And whenever you have negatives inside of trig functions, you should think about using the even and odd identities. Recall that our sine function is an odd function. Therefore, the sine of negative x is equal to negative sine x, right? Sine is an odd function. Therefore, I can replace sine negative y with negative sine y. This now leaves me with 1 plus sine y times 1 minus sine y. Let's now perform this operation. The problem is telling us to multiply these two quantities. When we multiply two binomials, we must use the distributive property of multiplication, or FOIL them, multiplying our first terms, our outer terms, our inner terms, and our last terms. We'll recognize that the outer and inner terms will actually add to 0, leaving us with 1 minus sine squared y. And 1 minus sine squared y, well, we've got groupings of 1s and squared trig functions. That should lead us to think about our Pythagorean identities. 1 minus sine squared y, we can replace that with cosine squared y. There is our final answer, what we were trying to get. Another one, sine of theta times cosecant of pi over 2 minus theta is equal to the tangent of theta. All right, so we're trying to get the tangent of theta. Well, what jumps out at us here? Okay, we have this cosecant of pi over 2 minus theta. Well, whenever we see pi over 2 minus theta inside of a trig function, we should think about using our cofunction identities. The cosecant of pi over 2 minus x is equal to, well, what's the cofunction of cosecant? That would be secant. So this is equal to secant of x. We can replace cosecant of pi over 2 minus theta with secant theta. So we now have sine theta times secant theta. Well, secant theta, using our reciprocal identity, is 1 over the cosine of theta. Sine theta times 1 over cosine theta gives me sine theta over cosine theta, and sine theta over cosine theta using our quotient identity, gives us tangent of theta for our final answer. All right, all checks out. Let's take a look at a couple more. Verify the following identity. Secant x minus cosine x is equal to sine x times the tangent of x. Well, if we're not sure where to go, never hurts to rewrite everything in terms of sines and cosines. Here I have secant x. I can replace that with 1 over the cosine of x. Well, the problem is telling me now that I need to subtract. And in order to subtract, I must get a common denominator. My common denominator is going to be cosine x. I multiply this by cosine x over cosine of x. That leaves me with 1 minus cosine squared x over cosine of x. 1 minus cosine squared, well, we've got 1s and squared trig functions, Pythagorean identities. This is sine squared x divided by cosine of x. Now, looking at what we need to get to in the end, we have to have a sine x out in front, so I can factor out a sine x from my numerator here and rewrite it as sine x times sine x over cosine x, which leaves me with sine x times the tangent of x, our final answer. Here, secant x minus 1 divided by 1 minus the cosine of x is equal to the secant of x. So you might recall in the last video I mentioned creating a monomial denominator by generating a Pythagorean identity. Here, in my denominator, I have a 1 minus a cosine x. Now that almost looks like a Pythagorean identity, but it is not a Pythagorean identity because I do not have a squared exponent associated with my cosine. All right. But one thing that we can do in this case is create a Pythagorean identity by multiplying this entire fraction by 1 plus cosine x over 1 plus cosine x. Notice that is the conjugate, right? I changed the sign in between my terms here. All right, and I'm allowed to perform this operation because this is the same thing as multiplying by 1, right? As long as I do the same thing to the numerator and denominator, we are in good shape, right? We're multiplying by 1. So let's see what happens when we multiply these out. Now, remember, when we're multiplying binomials, we're going to have to use the distributive property of multiplication, which means we are going to have to FOIL. Well, in my numerator, my first terms, I get 1 times secant x, that's secant x times cosine x for my outer terms. Well, secant x and cosine x are reciprocals of each other. Therefore, when I multiply secant x and cosine x, I'm going to get positive 1. My inner terms, negative 1 times positive 1 gives me a minus 1. So those are going to subtract to 0. And then my last terms give me a negative 1 times a cosine x. So that leaves me with secant x minus cosine x in the numerator. And in my denominator, first terms give me 1 plus cosine x minus cosine x. Notice the outer and inner terms again add to 0. And a negative cosine x plus a cosine x gives me a cosine squared x. So we are at secant x minus cosine x over 1 minus cosine squared x. And again, if you want, you can put parentheses around each one of those so that you can easily recognize we need to use the distributive property of multiplication. Okay, well, that just gave me a 1 minus cosine squared x in our denominator. And so we can replace that 1 minus cosine squared x using our Pythagorean identity with a sine squared x. Notice in the numerator, I also have a secant x. I can rewrite secant x as 1 over cosine of x. So 1 over cosine of x minus the cosine of x. Oh, notice that looks very similar to what we had in the last problem. What do we need to do here in our numerator? Let's get a common denominator. We multiply by cosine, this second fraction, by cosine x over cosine x. That'll give us a cosine squared x over cosine x. That's a 1 minus cosine squared x over cosine x, all divided by sine squared x. Okay, notice we have this entire quantity grouped in the numerator. And the numerator of the numerator is actually equal to sine squared x. And dividing by another sine squared x, well, that puts that sine squared x in the denominator with this cosine of x. Sine squared x divided by sine squared x, those are going to cancel out, leaving you with 1 over the cosine of x. And 1 over the cosine of x is equal to the secant of x. All right, it all checks out. Okay, so this first step that we did, all right, creating a monomial denominator by using a Pythagorean identity, not always obvious, okay, but if you see a 1 and a trig function that's not squared, you have a good chance at creating a Pythagorean identity. Just make sure we have to multiply the entire expression by 1. Now, this is not the only way to solve or prove this identity, okay? So a lot of these problems have multiple steps that will give you the same solution. So just because you didn't do this doesn't mean your way was wrong, right? But this is just one technique to look out for. All right, one more final example here. Verify the following identity. Cosine of x minus cosine y divided by sine x plus sine y plus sine x minus sine y over cosine x plus cosine y is equal to 0. All right, a lot going on here. Well, what is the problem telling us to do? It is telling us to add these two fractions. And if we're going to add two fractions, well, we've got to get a common denominator. And our least common denominator is going to be cosine x plus cosine y times sine x plus sine y. In other words, to get a common denominator, we're going to multiply the top and bottom of each fraction by the denominator of the other fraction, leaving me with cosine x minus cosine y times cosine x plus cosine y, notice that's the second denominator, over sine x plus sine y times cosine x plus cosine y, plus sine x minus sine y, sine x plus sine y, that's the denominator of our first fraction, divided by sine x plus sine y times cosine x plus cosine y. Again, all we are doing here is getting a common denominator. Now, when we multiply all of this together, again, we're multiplying lots of binomials, which means that we are going to have to FOIL or use the distributive property of multiplication. Okay, cosine x times cosine x, that's a cosine squared x. My outer terms, a cosine x times a cosine y. My inner terms give me a minus cosine x cosine y. So my outer and inner terms, they're going to add to 0. And finally, a minus cosine y times a plus cosine y gives me a minus cosine squared y. On our right side fraction, a sine x times a sine x gives me a sine squared x. Sine x times sine y minus sine y sine x. Notice again, the outer and inner terms are going to add to 0. And I have a minus sine y times a plus sine y gives me minus sine squared y. Okay, cosine squared x minus cosine squared y divided by sine x plus sine y over times cosine x plus cosine y plus sine squared x minus sine squared y over sine x plus sine y times cosine x plus cosine y. Now notice you could multiply out the common denominators, all right, expand these denominators if you wanted to. Is it necessary? I don't think so. It actually ends up getting a little bit sloppy, right? You've got sine x's and cosine x's, a sine x cosine y, sine y cosine x, sine y cosine y. Nothing is going to cancel or simplify, so these denominators are actually just easier to leave as is. So now that we have a common denominator, and we've simplified our numerators, let's combine these two fractions. All we need to do to combine our fractions is add the top and add the tops, and the bottom stays the same. That leaves us with cosine squared x plus sine squared x. So there's my plus sine squared x. And notice I've grouped the x terms and the y terms together. Minus a cosine squared y minus a sine squared y. Minus cosine squared y minus sine squared y. All right? Grouping our x terms together and our y terms together. And one thing here is both of these, cosine squared y and the sine squared y, have a negative in front. And so what we can do is we can factor out a -1 and group our x terms and our y terms together. Notice that leaves me with a cosine squared x plus sine squared x, Pythagorean identity, and a cosine squared y plus sine squared y. Both of those turn into 1. We have 1 minus 1 divided by sine x plus sine y over cosine x plus cosine y. Well, that makes my numerator equal 0, and 0 divided by any non-zero number is going to give us 0 for our answer, okay? Right, and there we have the proof of our identity. Again, just doing out the algebra here, okay? Following what the problem is telling us to do. If it's telling us to add fractions, combine fractions, get a common denominator, put them together. All right, that is it for verifying trigonometric identities. Make the left-hand side of the equation equal the right-hand side of the equation.